Testing. There we go. Alright. Alright. So, hi. Hello. Welcome, Fancy Meat Computers. Welcome to this, what might be your last class before the break. Hey, hey. Ho, ho, ho. The last class before you collapse on the couch in a fit of anxious exhaustion. And then get back up again because P1 is still looming over you like a dark cloud, like a Damocles sword. Oh, a 3DB3 tutorial? Do you really need to go? Okay, so, couple of things by way of announcements. Number one, did I do an official announcement about this? I don't think I did. I don't think I did. There was some belly aching going on Piazza, and oh my goodness, I've got such a backlog to get through. Project due date. Some people were asking if they could have yet another extension on Project 1, seeing as I've got it due on Thanksgiving Sunday, and some people are, occupied that day. So I replied with the meme, you get one more day. I will extend the deadline for Project 1 as far as Monday, but no further. You have one more day to do it in, so it has to be done by the end of the extended long weekend. But that, we do have to have some time to actually mock these things, So yeah, that's one thing of note. Get in there. There we go. Number two. I already talked about the final exam, so we don't need to talk about that. Okay, so number three. I hope y'all have got your COVID shot paperwork in order, because I got a pretty, a reasonably scary email from the vice provost last night. So this is my understanding of what's going on, and I'm telling you this so that you are A, aware of what's going on, and B, so that you can take the requisite steps that you need to take if you haven't, so you're aware that a problem is looming on the horizon for people who don't have their paperwork in order, / people who have not yet gotten their vaccinations. So the deadline for having your receipt of vaccination uploaded to the MacCheck system is October 17th. And if you don't have it if you don't have that in there at that time, then what's going to happen is that they're going to start unenrolling you from your classes. So right now what's going on is that the professors, such as myself, are being surveyed, and the purpose of that survey is to reallocate courses on Mosaic as to whether they are optionally in person or not optionally in person, right? So courses that are not optionally in person, people who don't have their paperwork together by the 17th will be unenrolled from them. Kaputski. For this particular class, I filled out that survey. I said, do not unenroll people because we can handle things online completely, which is true. I've set the course up for this matter. We've set this course up for hybrid distance learning versus in-person learning this semester. That's how we've been doing it. I think the majority of this class is doing distance learning at this point anyway. But yeah, just to let you know, the vice provost's letter, in no uncertain terms, said that there is no expectation on the part of the university that professors will accommodate students for distance learning for this purpose. So it's gonna come down to, whether the prof, uh, you know, it comes down to the decisions of the individual professors, and, whether or not you'll be unenrolled from some classes if you don't have your paperwork together by the 17th, that's going to depend largely on the professors. So, yeah, MacCheck is garbage. It won't even accept the documents I have uploaded. It just pens. It is pending. I'm not sure that you can use the word penned. You don't really hear the word penned used except as pending, It's not like you would, go down to the store and pend some merchandise, But, anyway. Well, GraphViz sucks. You suck. Ha. Got you. So, So, there are a few categories of people here that are going to be needing to be looked after. Number one, people who are not vaccinated and do not have an exemption. For you folks, my class, you should theoretically still be able to stay enrolled in it until the end of the semester. However, also in that letter, the vice pro, it's indicated in that letter that you will not have the same privileges in the winter semester, according to the university. So, yeah, I guess that's that as far as your post-secondary education goes. With respect to people who have their vaccines and have not uploaded the paperwork, that is definitely something that you need to do. It's not Mosaic, it's MacCheck as far as I can tell. You need to get the paperwork in, or else they're going to start unenrolling you from your classes, so get that paperwork in pronto. For those of you who have uploaded your paperwork and it's still pending, I would start rattling some cages in the administrative department, in the administrative wing of the university, to get that paperwork authenticated before the deadline. Regardless as to what, previous communications have said about, pending authorization, just getting it in for the deadline and not worrying about it being authorized by the deadline. It's ask the TAs how nice the university's administration is being about, pending, paperwork being pending, and basically just do, if you don't anticipate the university's desires before the university desires them, then you might find yourself left in the lurch. My advice would be to not trust official communications when they, specify leeway. Just deal with it immediately and as swiftly as possible, preferably in advance of any deadline, because 4 months ago they said that specifically they weren't going to require this, and now they do, and now it's it's increasingly heavy, so I would start, if my paperwork was still pending, I would start calling some offices and seeing if you can encourage it to go a little bit faster, because it's kind of a situation where things change so quickly that a policy decision can be made and enacted in like a week and you not even know about it, you know? So, anyway, just get your paperwork in order. But yeah. Yeah. So, you know, I don't want to dwell too much on this particular topic, but one gets the impression from listening to official federal and provincial government statements, as well as the statements of the university, that the policy is trending towards less and less tolerance of even the appearance of unvaccination. So get your paperwork in order. Anyway, so that's... Did you see how carefully I had to tiptoe around that? So let's talk about some actual lecture material today. Maybe we can get through most of this. We'll see. But yeah, so when last we spoke, yeah, if you will not be in Canada until the end of the year, like, again, I'm not one of the bureaucrats, so I don't know what their current policy is regarding people who are arriving, but I would suspect getting, like, proof, like, if you have had your vaccinations, whatever country you're living in, whatever receipt they gave you, see if they'll take it, you know? But, yeah. So, anyway. So, we were talking about, basically, we defined the rest of the UAE terms in pure lambda calculus, and then we were like, you know what, pure lambda calculus kind of takes a long time to do anything in, so why don't we just throw in, now that we've established that we can reestablish all of the stuff that we had in UAE in lambda calculus, let's just use it directly instead of having to refer back to the pure system all the time, because it is a little bit painful. Not sufficiently painful that that's not what you have to do for the entirety of assignment 4, but, you know, that's just the way the cookie crumbles, I'm afraid. So, Turing completeness and lambda calculus. We're going to talk about computability for a moment. So, just a reminder, I'm sure all of you know what Turing equivalence is, right? Like, well, I suppose some of you mathematicians who aren't in the computer science program might not know, but do you know what Turing completeness is? I'm about to explain it anyway, but I'll adjust the depth to which I explain it if you haven't heard of it before. So, to review, because this should be review, Turing equivalent is when a person is equivalent to Alan Turing. Ha! No. So, to review, a system of computation is considered Turing complete or Turing equivalent if it can perform all the actions of a Turing machine. The minimal set of things you need to be able to do is support conditional branching, which implies support for arbitrary go-tos, and you need an infinite amount of tape or memory. Okay, so about a third of the class doesn't know what I'm talking about. How about, do you know what a Turing machine is? I can't open another poll while the poll's still closing. So, technically speaking, no physical computer is Turing or can be Turing complete because of the constraints of physical memory. Do you know what a Turing machine is? I wouldn't have to ask this in an engineering program, because you'd all have taken the same courses. Cool. So, we've got, like, maybe one person so far who doesn't know what a Turing machine is. So, very rough overview. A Turing machine is, you have a tape with symbols on it. You have a read head that can either move along the tape, read, or write the symbols on the tape. That's a Turing machine. That's one of the earliest models of computation that was arrived at, and it turned out that was the one that was more physically implementable. So most of the early computers were based on the Turing machine model. It was sort of Turing. It's an interesting result because using so simple a system, it was demonstrated that anything that can be computed with that system, right? Which, you know, means that anything that can be computed with a computer, which is it's like a proof of the effectiveness of computing, of computers in general. But it was interesting because Alan Turing, is, I think I've mentioned this before, the student of Church, Alonzo Church. So, Church had come up with a different formulation of computation called lambda calculus, which of course we've been studying. So together, they came up with the Church-Turing thesis. The Church-Turing thesis states, a function on the natural numbers can be calculated by an effective method if and only if it is computable by a Turing machine. So that's the property that I was just talking about. The Church-Turing thesis is the effectiveness of the Turing machine at all computation. If it can be computed, on the natural numbers anyway, then it can be computed by a Turing machine. A secondary effect of this is that a program is computable via a Turing machine if and only if it is computable by a lambda expression. So this is an interesting, we don't really have the time or space to get into the Church-Turing thesis in any particular depth. You know, mostly, like, at an undergraduate level, it's out of our depth. But, if you're interested in reading about the Church-Turing thesis, I'm pretty sure they have it in the library. In Thode Library, there will be books that have the Church-Turing thesis in them. So, So if you want to read it, go read it. But yes, so for our purposes, what we're interested in is that there's an equivalence between a Turing machine and a lambda expression. That which is computable by a Turing machine is computable by a lambda expression, and vice versa. So, UAE, on the other hand, is not Turing complete because the theorem of evaluation holds. So, what does it mean what do we mean when we say arbitrary go-tos? One of the consequences of being able to perform arbitrary go-tos is that you can produce an infinitely running program that takes up a finite amount of space. So this is, it's, in order for something to be Turing complete, you need to be able to construct an infinite loop in it, right? Now this is an interesting idea, right? Because normally we think of infinite loops as being a bad thing. You don't want infinite loops. You want to avoid them at all costs because they're terrible, right? But without one, you can't actually compute everything that can be computed, right? So, in UAE, it's not possible to construct an infinite loop. Every step of evaluation leads to a new unique step in the evaluation, right? So you can't go back to a previous state inside of UAE. It's impossible. In order for a UAE term to take an infinite amount of time to evaluate, it would need to be infinitely long. So for a finite term, it's finite. This is a good property, but it also means that it's not Turing complete, right? So we can construct a finite Turing machine which runs infinitely, obviously. Yeah. So, yes. Any questions about that so far? Good so far? One vote no. Okay, well, what's your question? Okay. I think we're good. So, moving right along then. Curious constructions. Here's the thing about lambda calculus. The theorem of evaluation does not hold. This means that it isn't determinate. This doesn't mean that it's not determinate, because it is. Lambda calculus is determinate, depending on your evaluation strategy, of course. If you're using full beta reduction, it's not determinate. That's why full beta reduction is garbage. It's a garbage strategy. But if you're using something like call by name or call by value, in which like only one thing, like it's sufficiently determined so that there's always only one possible evaluation step that you can perform, it is determinate, right? We have determinacy in lambda calculus. But the theorem of evaluation does not hold. This means that you don't necessarily arrive at like a normal form after, you know, what am I trying to say? So the theorem of evaluation is that the thing will eventually evaluate to a form which cannot be further evaluated, right? That is to say, if you map evaluations, like the chain of evaluations is well-founded, right? You can map it to the natural numbers. It has a 0 point, right? It has a normal form. In lambda calculus, lambda evaluations are not necessarily well-founded. And we can show this very easily by examining a very curious entity called the omega function. So, the omega function is it's a lambda expression that reproduces itself. This is slightly different from the idea of the identity function, and you'll see that it looks a lot like the identity function. The identity function will echo back whatever argument you give it. What the omega function does is it actually physically reproduces itself. So it's lambda x, x applied to x, and then you apply lambda x, x applied to x to that, right? So when you evaluate that, you take the this one, f6, 3, there we go, thank you. You take this guy, you sub it in for x, and get rid of the lambda, and what are you left with? You're left with exactly the same thing again. When you beta reduce omega, you get omega right back. This is because these functions do not converge on a normal form, they are known as divergent. So that's an important piece of terminology. A lambda expression is convergent if it will eventually evaluate to one single normal form, and it is divergent if it does not, right? Even like you think of divergent as being like you know, the number of possibilities gets larger over time. But we also use the term divergent to express stuff that like only has one instance that goes off to infinity. But yeah, so divergence. The omega function is an interesting function, but it isn't very practical. It's the type of thing that you would put on a lecture slide during a third-year class on programming languages, but it's not something that you would necessarily use practically, right? However, its cousin, the Y Combinator, encodes general recursion in the lambda calculus. So the Y Combinator implements general recursion. This is how we achieve Turing completeness. We can produce recursion inside of lambda calculus. So the Y Combinator is lambda x, f applied to x, and then you apply that again. So you put it, effectively how it works is you put a function in here, right, at the end. That inserts it as, basically, like you take the two instances of x, which in this case is the, the same thing again, and then you apply that to itself and then apply that to f, and that, like, the lambda f inserts the function you're being recursive over at every level, because it's just going to get duplicated along with. But you can see the correspondence here to the omega function, right? All it is you've inserted an f there. Unfortunately, it only works under the call by name strategy. The following fixed point combinator solves the problem of general recursion for the call by value evaluation strategy. So fixed point is what we are going to be using in the example that we're about to do. Fixed point does this for the call by value strategy. Good. So let's talk about factorial. Everybody's favorite example of recursion. So recall the factorial function. N factorial is equal to 1 if n is 0, and n times n minus 1 if n is greater than, n times n minus 1 factorial if n is greater than 0. We can now encode it as follows. We'll call it g lambda factorial at lambda ftc lambda n. If n is equal to 0, then 1 else n times factorial n minus 1. So this is a strange hybrid combination of both lambda expression terms and terms from our enriched calculus. In this particular case, we're using mostly terms from our enriched calculus. To save time and energy, we are encoding this using the enriched calculus. Yeah, that's exactly what it just said. All right. So factorial is the fixed point combinator with g applied to it. Good. Still good? There's not much going on in the chat right now. Still good? Have I lost everybody? Has everybody buggered off for the weekend? Okay, so hopefully it'll make more sense once we go through the example. But again, forgot the difference between call by name and value. Ah, okay. So with call by name, you want the terms that your lambda you want the terms that you're subbing in to be fully evaluated, or at least in a normal form prior to them being subbed in. They're actually very, very similar, the name and call by name and call by value strategies. They're not very different. But yeah, the key point of both of them is that you don't evaluate past a lambda, right? You have to have a function fully applied in order to evaluate inside of it. But yeah, So hopefully this will make more sense once we do the example. So let's take the factorial of 3. So the way we write that is fix g3. Let's expand the fixed point combinator. So 3, there we go. Fixed point combinator becomes, it's lambda f, lambda x, f, lambda y, x, x, y, and you do that twice. Apply g and 3 to that. So applying g, of course, that g replaces f, and we get rid of the lambda. So there you go. And now applying 3, well, actually, what we're going to do first is we're going to set an intermediate variable just to make things easier. Thank God we don't need to use test and plus times functions. Expanding this would be horrid. Yes, this should be slightly easier to understand than the pure lambda calculus. Although I hope you understand why we did as much as we did in the pure lambda calculus. We had to like demonstrate that it works, and it's also all practice for performing the substitutions, right? Because performing the substitutions is like the main thing. That's the main idea. So let's set h equal to lambda x g y x x y, just for fun. So we'll need this one, so let's not compress that one, but let's compress this one down to h. So we get lambda x g y x x y h3. Good. So we apply h to x, so we get g lambda y h h y. So there you go. If we set factorial fct to lambda y h h y, then this simplifies down to g factorial 3. Right? So this doesn't seem like a huge, this has mostly been the setup. This is setting up the recursion. Now we get to actually expand the recursion. So if we expand g, we get lambda factorial lambda n. If n is equal to 0, then 1, else n times factorial n minus 1. We apply to that factorial and 3. So if we do both of those things in the same step, factorial gets applied to factorial, so that does not give the appearance of any change. And we're replacing n with 3, so that goes there, and there, and there. So we end up with, if 3 is equal to 0, then 1, else 3 times factorial of 3 minus 1. Doing 2 evaluation steps. First evaluation step is simplifying the if expression, so 3 is not equal to 0, so we select the second case. And the second evaluation step is we're evaluating 3 minus 1, that's 2. So we end up with 3 times the factorial of 2. Very good. So we expand factorial. Factorial yields lambda y h h y, so we have h h applying 2 as a result. So then we expand our instance of y, or it's not y, h, sorry. That gives us lambda x g lambda y x x y, which of course should look familiar. We apply h and 2 to that. That eventually leads us to g factorial 2. So you'll notice that we start with something like g. Where is it here? We start off with h. At some point we have h3, right? And then we perform a transformation and get g factorial 3. We start off with hh2. We apply transformations and get g factorial 2. This time we've got this this times 3 hanging off the front. So we expand this, once again and sub the things in. So if 2 is equal to 0, then 1, else 2 times factorial 2 minus 1. Evaluate that to 3 times 2 times factorial 1. Factorial 1 expands to h1. Then g factorial 1, we go back in again. 1 is not equal to 0, so, you know, etc., etc., etc. We eventually arrive at the value of 6. There we go. So this actually works. We have just successfully performed recursion. Yeah? Sounds good? Any questions? Or is it like, are we just so wiped from the week that we can't even scrape together the neurons? Okay. So, now that we've dealt that far with it, oh, we've got a question. Please type your question into the chat now. I'm a little confused, but you don't know what you're confused about. Well, that's, you know, that's how it goes sometimes, you know. So what's happening here? I'll explain it like in very, very broad strokes. The fixed point combinator allows us to package up the recursive function inside of a thing that duplicates it, right? Yeah, that's what I'm doing. So what fix does is it uses the self-duplication property of the omega function to also duplicate the duplicate instances of whatever function you put into it, right? So in this case, it's the factorial function that you're putting into it. So whenever we evaluate one layer of the factorial, we've set it up in such a way that we have we have some terms left over, and the terms that are left over evaluate the rest of it, right? Except, like, the difference is, of course, as you would expect with recursion, when you hit the base case, you return something that does not include the thing that's self-duplicating. So FCT, in this case, you'll see that when we set up FCT, remember that H and H are these very omega function looking things, right? When we set up FCT, what we're doing is we're like the self-replication gets packaged up in FCT, but what it needs in addition to being packaged there is it needs the G function to also invoke it, right? So when we do the else factorial n minus 1, when we do that, that's the bit that adds the self-replicating feature. If we just add 1, then we're not reintroducing the self-replication, so that halts the chain of recursion. But it's one of the ways that you can produce an infinite loop in lambda calculus the same way as you can in Turing, in a Turing machine, is if you miss the base case here, this expression will just keep on self-replicating infinitely off to negative infinity, right? which is very, like, it's exactly the same thing that happens if a while loop misses the base. Like, if you miss the base case that breaks you out of a while loop, it just continues on infinitely. It does the same thing, right? So hopefully that's an okay description. The idea is that you're packaging up the function with the thing that replicates the function, and so that the extra term is produced when it's evaluated. But yeah, hopefully that's okay. So let's talk about some formalities. Inductive syntax of lambda calculus. For the rest of this topic, we will examine the subtleties of a more rigorous definition of lambda calculus, beginning with an inductive definition of its syntax. This isn't going to be too much brain work because we already pretty much know how everything works here. There are some subtleties with respect to substitution that we need to go over, but the lambda calculus itself, none of this is going to be a surprise. So let V be a countable set of variable names. The set of terms is the smallest set V, smallest set T, such that V is a subset, T1 is an element of T, and X is an element of V, implies that lambda X dot T1 is an element of T, and T1 and T2 being in T implies that the application of T2 to T1 is also in T. Via this definition, we can define size and depth in the same way that we did under UAE. So you remember back in UAE, we defined, we drew an analogy between UAE and syntax trees and said, depth of a syntax tree is depth of a expression, and size of a tree is size of an expression. We can draw the same correspondence with lambda calculus. One new thing, however, that we didn't have in UAE is we have the idea of free variables. So we can define a new function over lambda calculus in the style of the const operator of UAE. Remember, the constant operator extracted any constant term, such as true, false, or 0, out of our untyped arithmetic expressions. In this case, we are extracting the free variables. So, if you have a variable, it is free. If you have a lambda x dot t1, the free variables of this expression are the free variables of t1 without x. Remember, this is set minus. And the free variables of t1 applied to t2, t2 applied to t1, is the union of the two sets of free variables of either of them. This should be a pretty natural definition of how we come to it. The one thing to, two things to keep in mind about this. Number one, once again, we are working with sets, so duplication is not a part of our definition. You can't have, if x is used 4 times inside of a particular lambda expression in a free manner, you're only going to get one instance of x showing up in the set of free variables because it's a set. That's one. And number two, notice the ability of a lambda to remove a variable from the set of free variables via set subtraction or set difference. You don't often see set difference being applied practically to things, so it's kind of interesting. So, I'm going to end that poll. There we go. So, use substitute. At the beginning of our discussion of the lambda calculus, it is said that it would be necessary... free here means not substituted by function parameter. Yeah, right? So, you remember... Oh, my goodness. Back at the beginning of lambda calculus, we talked about free versus not free. Yeah, free versus bound. So consider this, right? Lambda x, y. X is bound, y is free, x is free, right? Any instance, like anything that's being lambda'd isn't free inside of that expression. Everything else is. Ta-ra. So, at the beginning of our discussion of lambda calculus, we said that it would be necessary to develop a semantic of both the calculus itself and the substitution operation. Let's start with substitution. We will start with an intuitive definition based on our knowledge of elementary school algebra and develop a more robust definition by exposing issues with the naive approach. We'll go through 4 iterations of this. So, let's define naive substitution as follows. Subbing x, substitute x for s over x yields s. That should be obvious. Subbing x for s over y yields y if y is not equal to x. That should be also obvious. You don't substitute anything if there's nothing to substitute. X subbed for s over lambda y dot t1 is lambda y dot s subbed for x in t1. So substitutions pass through your lambdas, and x subbed for s t1 t2 is you perform the substitution on both of the subterms. So this is our, intuitive definition. Substitute is a move in Pokemon games, just so you know. I should have said, like, Pikachu used substitute. That would have been a better pun. This works reasonably well in most situations, such as the following. So x being subbed for lambda z zw in lambda y x yields lambda y lambda z zw, as you would expect. But this naive description contains a bug. Consider the following. What happens if we sub x for y in x dot x? We end up with x dot y. Oh, this is a problem. So we're turning the identity function into something that's not the identity function, which is, of course, not the way that things are supposed to work. X is supposed to be bound, right? Our substitution is not supposed to, it's only supposed to affect the free instances of x. This is not a free instance of x, so what we've effectively done is we've constructed a substitution that does not recognize the difference between free and bound variables. This happens because we pass the substitution through lambdas without checking first to see if the variable we're replacing is bound. Substitute is OP in Pokemon, yes. Substitute plus toxic. Plus Shuckle. Actually, I don't know if that would work very well. Anyway. If we fix the bit where we ignore bound versus free variables, we end up with something like this. So everything's the same except for the bit where we're substituting around the lambda. If y is equal to x, then we leave it alone, right? So if the variable that if the thing we're replacing is the thing that's being lambda abstracted, then we just stop. Otherwise, we pass through the lambda, right? Pikachu can't legally learn substitute, but Mimikyu can. Yeah. Oh man, like that ability where Mimikyu gets the first hit free plus substitute? Good lord. Good lord. Anyway, so now the former this instance that we were having a problem with earlier, that now works the way we expect it to. So if we're subbing x for y, lambda x dot x is still lambda x dot x. We recognize the boundness of x. But the following doesn't work. Let's say we wanted to sub x for z in lambda z dot x. We end up with lambda z dot z. When we sub in z in this instance, it becomes bound to the lambda. This is known as variable capture. Just like Pokemon. See? It wasn't just random nonsense with Pokemon. I had a plan the whole time. We were talking about variable capture in the same way that Pokemon are variables and you capture them. Alright. So that... Oh. Ha. It's 1:20. I guess we will continue this when we all get back from our break. That will be entirely too short to get anything accomplished in, I'm sure. Anything meaningful, anyway. So, yup. Very good, very good. That's it. That's all, folks. Yep. If anybody hasn't seen the meme video, one of my students in my first year class made a meme video of me during my lectures, and it's quite funny. So if you have 4 minutes to spare today, I would recommend checking it out. It's funny. It's kind of funny watching yourself be memed, because it's like the things you think about you that are funny are not the things that other people think are funny about you. It's like weird pauses apparently are the most funny thing I do. But anyway, will there be a meme video for this class? Well, I don't have time to make one, but if somebody else wants to make one, be my guest. Yep. You have plenty of material. There is, oh gosh, probably at least 200 hours of me on the internet right now that you could use as source material. I'm sure there are some good nuggets in there. Yeah. Does anybody have any questions? Too many assignments, not enough time. Isn't it always the way? I also don't have time to make one, so also it seems just kind of wrong for me to make a meme video of my own lectures. People might start thinking like, oh, he's just acting goofy so that he can get extra views from meme videos. But no, I don't act goofy so that people make memes. That's a recent phenomenon. I've been goofy for far longer than this, as I'm sure all of you know. Tired today. Maybe the next time Felix has a nap, I'll join him. Alright. Have a nice break, everyone. Try not to go crazy. I'll try not. I will try not to go crazy as well. Take her easy.